In this video, I'm going to go over the application infrastructure for Rentalcore. It's going to be an overview of what the application infrastructure is, and there will be other videos that will go more in depth and actually showing the different pieces of the infrastructure working and how to manipulate them and how to develop upon them. The whole concept of our infrastructure is built on this infrastructure as code, so that pretty much every part of our infrastructure is defined using code. Yeah, as you'll see throughout this, we're virtualizing everything, including the development environment, so that we're able to basically define the infrastructure using code instead of physically manipulating servers and going in and manipulating, setting up different operating systems. So let's get right into it. So we started with these requirements. We wanted the whole application to be scalable, ideally without having to go offline to scale it. Reliable, so that we're failing over when certain nodes or servers fail, or clouds in general, cloud provider fails. We also wanted to be able to provide some load balancing, so that if one portion of the infrastructure is getting hit really hard, it will load balance to other cloud providers, other nodes, other node clusters. Minimal ramp-up time for developers. On projects I've worked on in the past, there was a lot of documentation around just setting up the local environment. And there were a lot of particulars about setting up the environment depending on which operating system you were developing in. So with this project, I really wanted to be able to create something that required minimal ramp-up time, and we had a pretty good chance that it was going to run the same no matter which operating system you were in. And there's basically two ways that you can go about that, or three ways really. You could have no local environment and everything is really hosted in the cloud, and users are using some cloud-based IDE to actually do their development on, which maybe that will be something that's popular in the future, but right now I don't think that it's developed enough to warrant actually using for this project. The other two options are virtual machines and containers. So there are pros and cons to each, and I think I will cover those in depth in the next slide. So continuous integration and continuous deployment. That basically just defines how things get moved around to the different environments. With the current rate of being able to change the application on the fly within minutes or hours, has become much more popular with development. You'll see like Amazon is changing their website every second, and they're using continuous integration and continuous deployment strategies to do that. So we are also using some tools to do that, so that when developers push their changes, they don't actually need to worry about pushing them to testing manually or production. Their changes automatically get built, tested, and deployed to whichever servers they need to. Some things that were nice to have. Number one is being cloud provider agnostic. As times change, certain cloud providers are going to get bigger, some are going to disappear entirely. We don't necessarily want to be locked into any one cloud provider. There could be a pricing reason for that, but it'll just be really nice for us to be able to move from one cloud provider to the next, or even fail over between multiple cloud providers in the case of an outage, which does occur. We've seen Amazon Web Services go down, and many huge sites like Netflix go completely offline because of that. Yeah, I think that maintaining that cloud provider agnostic, or being cloud provider agnostic, is very nice to have if possible. Yeah, and you'll see how it is possible in the next couple of slides. Yeah, similar to that is just using multiple cloud providers for failover and load balancing, which being cloud provider agnostic allows you to do that when you're not relying, you don't care which cloud provider is serving your data. You just know that there are cloud providers that are basically providing the resources there. So that brings us into what we are using for Rentalcore, and that is containers. We are using containers in all aspects: the local development environment, the testing environment, as well as the production environment. everything that is running and publicly accessible for Rentalcore should be running in a container. There's a couple of reasons for that. Number one is that it allows us to be cloud provider agnostic. Because containers can move back and forth relatively easily from one physical piece of hardware to the next, it really lends itself to being cloud provider agnostic. It also allows us to be scalable without going offline. The main reason for this is that when you're building services in containers, you need to assume that that container is not going to live forever. You need to assume that the container can die at any time, and that another container is going to pick up the load or the responsibility that that container had. And just that concept, that mentality of always having a failover container or assuming that a container is not going to live forever really lends itself to being able to destroy containers without the application going offline, being able to likewise scale containers without the application going offline. And I'm sure that you could achieve the same scalability without going offline using virtual machines. However, containers boot up a lot faster. The caching functionality with containers lends itself very well to quickly destroying containers and bringing them back up. Yeah, it's just a lot faster than virtual machines, and lighter weight as well. Which, yeah, just the memory footprint for a container can range from like 1 megabyte up to entire operating systems running on them, which is not something that you can achieve with a virtual machine. One of the biggest things is that it guarantees that the code runs the same in development as it does in testing, as it does in production. It lets us really, really closely mimic production. You could probably reach a similar level using virtual machines. However, the resource requirements on a development machine are pretty vast when you're talking about the number of services that we are running. It allows us to define the layout or the way that containers are talking to each other using code. So we can actually define the services that we want to run, the services that they're able to talk to, the data that they're able to share between containers using code. So we're basically writing YAML, and we're getting an infrastructure. The code that's being used to define the development environment is very, very similar to the code that's being used to describe the production and testing environments. And because it's so similar, we're very closely able to simulate production on a local machine. So these are the services that we're using. So at the top level, we're using Nginx to provide the reverse proxy, as well as the top-level load balancing to another set of load balancers, which we'll get into. Nginx is also handling the SSL termination, so that all of the other containers below Nginx don't need to really worry about translating data or decrypting the data. Nginx is also serving static or semi-static files, like images, the favicon, documentation. So documentation, some of it is being generated on the fly, or not on the fly, but at compile time. And some of it is just completely static. That's just being loaded right from Nginx. Some of it's actually being pushed into Nginx at compile time. HA proxy. So HA proxy is the next step down, and that's providing the load balancing to all of the different API or web service nodes. So that's all. APIs are I'm treating the API layer as all of our code that's running. You could refer to them as the web services as well, but that is our code running in Node.js. So the reason I'm using HA proxy in between Nginx and the API layer is that HA proxy has a very good system for automatically associating new instances without having to reconfigure HA proxy and restart it. So it does that for new instances. It also automatically knows when an API instance has died, and it will no longer route traffic to it. So it's quite a bit smarter in that aspect than Nginx is, at least in our use case. Nginx as kind of just serving as a dumb load balancer that always assumes that the HA proxy load balancers are up. Now, if we do scale the number of HA proxy load balancers, we do need to update the configuration file for Nginx. Or not update it, I'm sorry, just redeploy the Nginx. It'll automatically associate the new instances or fewer instances of HA proxy. So the next level is the API level, so that's what's running our code, and that is what most of our developers are going to be concerned with. That's also the repository that most of our developers are going to be working out of. So pretty much each of these service layers is going to have a repository associated with it under our company organization, with the exception of the HA proxies. And the reason being is that we're not actually doing anything special inside of the HA proxy outside of just loading the configuration files. So there's no reason for us to have our own repository and build those images manually. We can just rely on the HA proxy developers at the HA proxy company to push out their new Docker images as they release them. So after the API layer, it kind of forks. There's two different types of databases. The relational databases have another HA proxy load balancer in front of them, and that just automatically associates new relational databases as they come online or go offline, and the API doesn't really need to be concerned with how many of those there are or how to even reach them. It just needs to be concerned with sending its requests over to the DB HA proxy, and then that will route the traffic accordingly. Now we'll get to this in a further video, but the relational database is a cluster of masters. It's not a master-slave relationship, and that's the reason that the API doesn't care about which database server it actually hits. It can hit any one of them to read or write, which is pretty awesome, and it's something that has really only come about in Docker, as far as I know, with MariaDB and Galera cluster. So that's where a brunt of the data is going to be stored. That's where all of the company data is going to be stored. There is another database service that we're using, and that's a NoSQL database service running Couchbase, and that's another master cluster. And that database cluster is going to only be responsible for credentials, authentication, and user configuration settings. So these are going to be user-specific settings that will get loaded in and out. And that's kind of going to be used as a session database. So the code lifecycle. So I'm just going to quickly describe how do we get code from development all the way up into production. So in our development environment, everything's running inside of Docker. You make your changes using whatever IDE you want. You push those changes using Git to our GitLab server. GitLab is going to, that's the step here now that I'm on, GitLab is going to build all of the required Docker images based on the GitLab configuration file, or CI configuration file. It's going to name all of these Docker images with a reference back to that commit, which Docker calls or GitLab calls a build number. That way, once we're in testing, you can see exactly which you can associate the image that's running in testing with the actual commit that generated that image, so that we can more quickly debug problems and see where they came from. GitLab is also going to run unit tests and integration tests. If any of those fail or don't meet the requirements, it will fail at that point and not push any further. So that ensures that, well, it helps ensure that broken code does not get pushed to testing and production. And there are certain rules around coverage as well. So if we don't meet a certain threshold on the number of unit tests or integration tests that are written for how much code they cover, then it will fail for that reason as well. So that's not a blatant failure, but it fails to meet our requirements. So at that point, it will push the image to testing. Testing will automatically reload or redeploy those containers using the latest image. Production will not. Production is currently anyway a manual process for choosing which version of the images we want to run. And that's for a very good reason. This is all new to a lot of us. So we don't necessarily want to automate every single portion of it. And until we get through with serious testing, it probably doesn't make sense to push things to a production server automatically. It's a simple enough task to actually go in and update which version of the application the production server is running. But yeah, we will look into actually deploying those automatically in the future, either based on a certain number of people signing off on the build or something like that, to be determined. So in the testing environment, so I mentioned that the testing environment will automatically run that image, and so every time that an image gets updated, it will automatically redeploy whatever containers rely on that image using the latest image. You can also push directly from development to testing, and I'll go over that in a later video. There will be a troubleshooting video where I'll go over some troubleshooting Docker commands. It's definitely not best practice to push directly to testing because that will allow you to push images that don't pass integration tests or unit tests. So that is really for just serious debugging of testing. Production environment. So I mentioned that we manually have to choose which image is running in development environment. It doesn't automatically redeploy containers based on images being updated. Because we're tagging these images with build numbers, they're going to stay in our Docker image registry for a very long time, which means that we can always reference or roll back to previous images if there is an issue in production. Same with testing. You can roll back to a previous version or 20 versions ago if you really need to, pretty quickly, pretty easily. In testing, it was roughly 15 seconds per container. That might change as the application becomes more complex. But yeah, right now it's around 15 seconds per container to redeploy. And it's a rolling deployment, so redeploy does not mean that all of the containers go offline and come back online with the new image. It means that they go offline one at a time and come back online one at a time, which ensures that the application is never offline completely. It might just be in a kind of limp state where there aren't as many resources as there were before it started redeploying. So the continuous integration deployment cycle. So we're using GitLab for versioning, we're using GitLab for code review, as well as the continuous integration and continuous development. To a certain level, it's also being used for the testing in that it's running those tests as part of the continuous integration and continuous development. Those tests are also running on local machines automatically. So every time that you make a code change locally, you're going to see an update with your coverage results and the integration and unit tests results. So gitlab-ci.yaml is the YAML file that's actually defining the continuous integration and continuous deployment environment. It defines the different stages that are being run, which are all listed over here currently. We can add or subtract to those stages as we need to. These stages aren't necessarily processes. There can be multiple processes being run in parallel in each of these stages. However, the actual stages themselves do not run in parallel, so that a previous stage like build must pass before test is run, and likewise test has to pass before the release stage will actually occur. That one will happen. These two are going to happen more often. It should be rare that the release stage fails. That would only happen if all of the cloud providers are offline at the same time, which I hope never happens because that means that a majority of the internet is offline. GitLab does provide us with some notifications based on builds occurring, builds failing, builds succeeding. It will email the admins if a build fails completely or fails for any reason. So at any stage level, a failure causes a build failure. We also get updates in the Slack channel, which actually is not the server's channel. It is the notifications channel. The server's channel was removed since we're not actually running any servers in particular. So yeah, so you'll see notifications about deployments, if the production environment changes, if the staging or testing environment changes, if something gets committed, if some build starts, if some build fails, if some build completes. You'll see all of that inside of the notifications channel on Slack under our organization. So if you need to see, because you're debugging or something like that, the results of all of these stages, under GitLab there's a section under each project called pipelines. And under pipelines you'll see the results of all of the different commits and their processing through these stages. So you'll see what stage it failed in. You'll see how long it took to run. If you actually drill into a pipeline, you'll be able to click on each of these individual stages and see the actual console output of that stage, which is very helpful if you're not sure why something failed the build stage. You can go in and see the actual console output and see which step it failed at, why it failed, generally why it failed, depending on the verbosity of the service that you're actually looking at. And then you can also see the build number that matches up with that commit, so that you can link the image in the Docker repository to, or Docker registry, back to whatever this was, this pipeline. So that brings us into the actual architecture. So this is what the architecture looks like for the development environment. And this is running using Docker Compose. So there's another YAML file in the project that's defining this environment. The ones that are grayed out are not enabled by default, but you can enable them by manually going in and changing the Docker Compose file. So like I went over earlier, we have the Nginx container providing the top level load balancing as well as SSL termination. It is providing SSL termination in development. It is a self-signed key, so you will get an error when you go into your browser the first time saying that it's an insecure connection. That goes down into HA proxy, which in the development environment, there's only one of each of these due to resources. In the testing and production environment, we'll see that there are more than one of these for failover. And by default, there's only one of API and only one of Couchbase, and so on. So HA proxy will route to whichever API containers are enabled. You can certainly enable 2. You can enable 20 API containers on your machine if it has the resources to handle that. And I'll show in a later video how to actually go about doing that, so that you can more closely simulate production, because production does rely on that failover. So if you want to test the failover states, then I'll show you how you can do that. So I mentioned that we had 2 different types of databases. We have the NoSQL Couchbase database cluster, and then the MariaDB Galera cluster for relational database management. So the API actually handles the failover and load balancing between the Couchbase instances. With MariaDB, there is no such thing. So db-ha proxy is the container that's responsible for load balancing and failing over all of the MariaDB database containers, which there's only one to start with, but you can certainly scale it up to 3 or more. Just make sure that it's an odd number, otherwise you will run into issues with the split brain problem on databases. Same with Couchbase. That should always be an odd number of instances. So testing environment architecture. So it gets quite a bit more complex from the development environment to here, because now we're dealing with cloud hosting. So this could be any cloud computing provider. Right now we're using Amazon Web Services. Inside of the actual cloud provider, we define a cluster of nodes. So we could have multiple clusters of nodes under the same cloud provider, but they basically just define a group of instances on that cloud provider that we can assign like services to or tag services to. So you'll notice in testing we have one node cluster up here. Inside of that node cluster we have two separate nodes. So each node is a single instance on that cloud provider. So this would be a single instance on the Amazon EC2 service. Inside of each of those nodes we have those containers running, and they're wrapped in these services, these service layers. So even though these two Nginx containers are on two separate instances, which could be in two separate data centers, they're able to speak to each other using this Nginx service layer that Docker Cloud actually generates. Because it's actually creating a network, a virtual network, with whatever containers we decide on. It could be multiple networks. In most cases, I think it's a single network, but we will definitely be looking at separating the databases into their own network in the future. But yeah, so even though these things could all be in different parts of the world, they're still able to talk to each other as if they were locally in the same place. So we are providing failover at the very top level using floating DNS addresses, so that when you hit api.rentalcore.com, you'll actually see two DNS records being served, and those two records will go to either one of these, which provides us some failover at this level, so that if Nginx 1 goes down, you still request the same domain name. You don't have to request some subdomain to get to the other top level load balancer. It just automatically routes over to that load balancer until the Nginx 1 comes up. Or if we add an Nginx 3, then it would add that to the pool. Same with all of the other services. So from Nginx 1, we're able to reference just the HA proxy service, and it will automatically load balance for us between these two, or 3 or 4, however many there end up being. Right now there's only 2. But yeah, that lets us basically fail over between nodes, between instances, even though they're physically separated. But they could be physically separated. Same thing with the API containers. They have their own service as well that HA proxy is referencing, so that provides us some level of failover there. And then, like we've seen before, API can either talk to the relational database service using the proxy there, or it can talk directly to the NoSQL Couchbase instances by referencing Node is actually referencing these instances one at a time. It's not referencing the service as a whole. We could potentially change that, but the way that the Couchbase client is written for Node in particular, it assumes that you're going to be connecting directly to the instances themselves. So you notice that there are a couple of different node clusters. So we're actually separating the databases into their own separate node clusters because their resource requirements are quite a bit different from the other services. All of these services have fairly minimal resource requirements. Couchbase in particular uses a version of memcached to load the database into memory, so it's got pretty substantial RAM requirements. And because the relational database is going to be our main data store, that's going to have some different storage requirements than the other containers. So these are built in such a way that any one of these containers can die and be replaced without having to reload data from some outside source. The databases themselves do not have that, so we are backing up production anyway to local machines in each of our server closets, and we'll see that on the next slide. So this looks pretty daunting, but it's essentially the same thing as the testing environment, just doubled up so that we have failover across cloud providers. So this doesn't have to be DigitalOcean and AWS. In this case, it's Amazon Web Services and DigitalOcean as the cloud providers. But as you can see, those service layers will actually span across multiple cloud providers, just the same way that they span across multiple instances inside of a cloud provider. So because each of these node clusters are separate, we're able to scale these independently of each other. So we could scale up our Amazon Web Services, maybe because it's cheaper. We could scale that up to a greater number of instances than our DigitalOcean deployment, where maybe DigitalOcean just serves as the backup for worst case scenario. But yeah, so right now, anyway, there's communication from one cloud provider to the next. In the future, we would like to limit that communication to only occur if need be, so that data isn't going in and out of the network. Because to get from Amazon Web Services to DigitalOcean, you'd definitely have to hit the public internet to get from one to the other. And that's not necessarily good for latency or security. So we really want to limit it to staying even geographically on a certain Amazon Web Services data center if we can. But currently that is not happening. So you could literally take down every single container in Amazon Web Services, and it would all route over to DigitalOcean. You could remove all of the HA proxy containers from Amazon Web Services and still hit these Nginx containers in Amazon Web Services, and they'll route traffic over to DigitalOcean. So that's pretty cool. So we literally would have to break almost every one of these connections for the service to go completely down. So something that you'll notice at the bottom that's different than the testing environment are these on-premises on-premise servers. So these are Synology servers running in each of these different cities and branch offices, and they are just there to serve as the backups for the databases. Since, like I said, the databases could die and lose their data, we needed some way to store them permanently. So there's a live backup of each, the Couchbase NoSQL cluster, as well as the MariaDB Galera cluster. And they're backed up live on different servers so that there isn't a substantial load on any single location. They're also backed up hourly, daily, weekly, and then yearly. So that at any one given time, we'll have, once we hit 10 years running, we'll have up to 10 years worth of backups at an hourly, we'll have up to 10 years worth of backups. Yeah, so this is, you'll see where when I mentioned that the database clusters need to be deployed in odd numbers. That's why you'll see like 2 nodes that only have a single instance on them, and that's why it's kind of a waste of resources, because we can't, I guess we could possibly plan to always push the odd number to a particular node so it uses less resources, but right now we're not. Each of these nodes are exactly the same in their resources from Amazon Web Services and DigitalOcean. Stack orchestration. So how are we actually managing all of these containers, keeping them running, replacing them when they die, just deploying them in general? How are we actually pushing the API images, the MariaDB images to all of these things? So we are using Docker Cloud for stack orchestration. It allows us to define that environment. So I'm defining this entire environment using another YAML file, which is very similar to the same YAML file that's being used for the local development environment. And it allows us to define all of those services, define the containers that belong to them, even define, using tags, which types of instances or node clusters they should be served in. So we can say that all of the API instances should always be served in Amazon Web Services on the West 2 data center. Or we could say that half of them should be deployed on West 2 and half of them on East 1. We can do whatever we want there. Something else that's kind of cool is that we can actually tell it to use all of the available nodes. So with Nginx in particular, because it's bound to port 80 and port 443, we can only have each Nginx instance on a single instance, or each Nginx container on a single instance. So there's a rule in there that's basically saying however many instances there are, or nodes there are from the cloud provider, put a container of this type on every single one of them, so that as we scale up the number of nodes that we have with, say, Amazon Web Services, the number of top-level load balancers also increases automatically. So if we add 3 more nodes to our Amazon EC2 instances, we automatically get that many more Nginx containers. Yeah, it also, so using this YAML file also allows us to define things like environment variables, other types of, which are all used for configuration. So we're able to change the configuration pretty easily from production to testing to development without having to rebuild those Docker images. So that is an overview of the application infrastructure. Hopefully you learned something and it will be helpful while you're developing the application. But yeah, keep an eye out for future videos, which will be showing more about how to actually use these different services, how to run them locally, how to configure them locally, and how to develop upon them. Thanks.